Hello, everyone. Today, I would like to share with you a topic that I have long been interested in, but only recently got the chance to explore more fully, mathematically speaking. Yes, today I will be talking about group theory in the context of particle physics and the symmetries of the standard model. So, what is group theory? Well, group theory is the study of groups, objects that satisfy certain properties and allow us to represent pretty much anything. Today, however, we will be focusing on symmetries and transformations. If you spend any time on the quantum side of Wikipedia, you may know about the SU3 times SU2 times U1 symmetry of the standard model. This will be our main topic of discussion. I would like you to keep Noether's theorem from classical mechanics in mind, specifically the connection between symmetry and conservation. That will come up only towards the end, but I feel like it is a good thing to consider, right? So, what is a group? The definition you may have heard thrown around is that a group is a collection of transformations, for example, rotations, translations, under which some object is symmetric. Likely, this explanation was accompanied by a Rubik's Cube. Indeed, this is true. When put into more precise terms, a group is a set with some operation that takes two elements and produces another element inside the group. This is called closure under multiplication, though it's not the same multiplication you may be used to when we basically put things in a grid. First grade. Um, Now, this operation that we call quote unquote multiplication must satisfy some properties you may be used to by now if you've hung out in kind of mathy circles. So the first is associativity, which means it does not matter in which order you apply the operation, right? A times B parentheses times C is equal to A times parentheses B times C. There's an identity element present, right? So A times some identity I is equal to A. And an inverse is present. So A times A inverse is equal to I, the identity, and A inverse times A is equal to I as well. So let's get ourselves a little bit more familiar with groups by proving a relatively basic theorem to get a bit of a feel of groups, right? So let's prove that inverses are unique. Here we start with our initial assumptions, right? That there are some two inverses, A inverse 1 and A inverse 2. So let's rewrite A inverse 1 like this, right? This is effectively just showing that an identity element exists, which we know from the previous slide. We can do this. Next, we substitute this relation, our second relation, that includes A inverse 2. Then we use associativity to regroup these. And finally, we use our initial relation that A inverse 1 times A is equal to the identity element. And finally, bring it all full circle to show that A inverse 1 must equal A inverse 2. And this proof is very general. We did not explicitly define A inverse 1, A inverse 2, which means it is then usually when we are talking about inverses, we talk about the inverse of an element, not an inverse of an element. Okay? So another concept that is important is that of subgroups. Subgroups are just subsets of the original group that are also closed under multiplication. So every result of every multiplication is also in the subgroup and contain the identity element. Something which will come up later is invariants. Invariant subgroups are subgroups which can be transformed or multiplied by any element of its parent group and its inverse and still be part of the subgroup. If you're familiar with the linear algebra, a specific case is A inverse is equal to B. So more generally, in our case, it would be A inverse equals C, where both B and C are in the subgroup under consideration, right? So you may wonder how symmetries, let's take the example of Rubik's Cube, for example, right? Fit into this. What I described above is the most general definition of a group there is. Even the rational numbers under the operation being multiplication form a group. What we are interested, however, is symmetry groups, right? So a Rubik's Cube does not fundamentally change. It is still the same thing, right? You don't get a slice of pie by rotating a Rubik's Cube, which is why the rotations you can do to a Rubik's Cube form a symmetry group. So every symmetry group belongs to a mathematical object. Given a mathematical object, we can find its symmetry group, right? Intuitively speaking, just with the Rubik's Cube example, that can be rotations, that can be translations in space, right? So symmetries are things you can do to the mathematical object without it changing. For example, a sphere can be rotated any way you want, and you won't be able to tell. This is a rotational symmetry. Furthermore, since the angle and axis can be chosen arbitrarily and the angle can take on any real value, we say the symmetry is continuous. So continuity will come up a little bit later when we get into the particle physics aspect of all of this. Objects inside a symmetric group are transformations. They can, for example, be described as functions or matrices depending on specific object that you're looking at, whatever they may be mathematically, however. The important part is how you think about and use them. The operation on the group is a sort of combination of two transformations. You can think of it as doing one after the other, if you would like, or just kind of matrix multiplication, adding functions, right? Take the time to convince yourself that associativity holds under this interpretation or whatever other interpretation you may like. At least for some like basic shapes. So cubes, spheres, right? Translation, rotation, things like that, just to get kind of a grasp on what we're going to be talking about for the rest of the video. Okay, I assume you have done that, so let's move on. So the intuition behind invariant subgroups. Back to invariant subgroups, you may ask, doesn't invariant imply unchanged? What about this group is unchanged? And that is a great question. So what remains unchanged is the overall structure. Coming back to our similar matrix example, the parent group element G in G and G inverse in G can be thought of as a change of basis or a shift in perspective. To be an invariant subgroup means that the shift, even if it changes what we're seeing, still belongs to the same subgroup or plane. Perhaps it's not a very good example, as change of basis is a very particular, um, transformation, which which maps one matrix onto itself, basically. But I feel it is a good way to think about it, and it is possible to extend that kind of understanding, if you already know a bit about linear algebra, to group theory. Yeah. So this, in my opinion, becomes even more understandable when you consider symmetric groups. Since by definition, an object remains symmetric, whichever symmetry transformation is applied to it, invariant subgroups can be thought of as just any other group that are also well behaved when combined with elements of the parent group, right? So to apply what we just learned to the standard model, we will also need to understand what the symbols SU3, U1, but also SON and ON mean. So these SON and ONs will not come up explicitly, but they are very closely related and can also be transformed into the unitary groups, right? SU3, etc. These are symmetry groups, which you may guess satisfy either unitarity or orthogonality respectively. The S in SU and SO is for special. These groups are the invariant subgroups of the U and O groups, so unitary and orthogonal. If you're a bit familiar with quantum mechanics, you may know the concept of unitary operators. These are present in the Schrödinger equation and act to ensure basically that the total probability of every state never exceeds 1. Right? Because we can't have a particle be in more than one state after we measure it, basically. The unitary group UN then is the group consisting of n by n unitary matrices, um, where these matrices satisfy U star U equals U star equals the identity. where U star is the complex conjugate of U. So basically the transpose and complex conjugate every single element within U. Basically, there are matrices where the complex conjugate is also the inverse, right? Like this is very similar to the inverse relation. Orthogonality, likewise, is a condition on the matrix inverse as well, where O transpose O is equal to OO transpose is equal to the identity. And hence, the orthogonal group ON is the group of these n by n orthogonal matrices. Now, you may be already noticing a similarity between unitarity and orthogonality, and you would be correct. Orthogonality can be thought of as the real valued equivalent of unitarity, and it is, I believe, quite useful once you get a little bit deeper into the mathematics of it all to kind of consider how unitarity and unitary groups can be transformed into orthogonal groups through homeomorphism or isomorphism. And in general, it just provides a different way to think about things, which I believe is always useful when learning if you get stuck, right? So why exactly does any of this matter? Well, remember that all of these groups, SU3, SU2, U1, etc., are all symmetry groups of the standard model. Further, remember that these matrices represent transformations. We are left with the following conclusion that can be summarized that the standard model is symmetric under unitary transformations, which preserve probabilities and information as the determinant of these special unitary matrices is 1. Typically, the symmetry of the standard model is written as SU3 times SU2 times U1. The reason for this separation is because the three groups are due to different forces being symmetric in different ways. SU3 is due to quantum chromodynamics, so color charge symmetry. So within hadrons, like protons and neutrons, there are quarks, and these cannot exist on their own because they have a color charge, and color charges must always remain neutral. You can look into gluons if you would like. It wouldn't necessarily be beneficial to understand just like this math, but it is a very interesting topic. So in hadrons, there's 3 quark colors, right? And there's 3 quarks, and each of them has one of these colors. So red, green, and blue, and they cancel each other out, right? Kind of like a computer screen. You may then assume that this SU3 symmetry is due to there being 3 colors, and indeed you would be right. Inside a hadron, we can change or rotate or transform the color charges of the quarks, and the dynamics would remain unchanged. In fact, as I mentioned, this is exactly what is happening all the time due to gluons. So you can think about this unitarity determinant is one condition as there's only one level of color charge, right? Such a symmetry would not add or remove charge, right? There's no such thing as 1.5 red charges. That's just not defined in standard model, and it makes no sense. So the symmetry is important because it illustrates something called, that's odd. Anyways, next factor, SU2, comes from the weak force. This force governs decay and flavor. It's the force that allows the heavy tauon to decay into lighter electrons and muons. All of these are leptons, but have different flavors. The symmetry, however, arises from different possible decay chains or branching fractions, whatever you want to call them. So tau decay chains, taken from the Particle Data Group's website, which is honestly an invaluable resource for kind of self-learning and trying to understand publications, especially. We know that a tau can decay into, among other things, a tau neutrino electron and electron antineutrino, and a tau neutrino, muon, and muon antineutrino. But of course, a tau cannot decay into a tau. That wouldn't be decay. In fact, you'll find that the SU2 symmetry comes from these kinds of replacements, which are equivalent from a physical point of view, right? And this symmetry is so universal that it illustrates something called lepton universality. This property means that the universe does not favor any lepton flavor over another, and as we will see, causes different flavors of leptons to be equally present in various decay chains. Right? Back to our decay chain here, 17.82% and 17.32%. This is almost the same, right? It's basically experimental error. An interesting point in the symmetry of the weak force is a breaking of chiral symmetry. Chirality is the handedness of a particle, while left-handed particles interact with the W plus or minus bosons. Right-handed ones do not. If they did, another SU2 factor would be added to the symmetry. In fact, a lot of symmetries are broken by the weak force. Recent developments have shown isospin symmetry breaking, differentiating up and down quarks, which are present in protons and neutrons. So that's quite interesting, keeping up with all of this new research. Now on to our last term, which represents electromagnetism. So in its simplest terms, U1 can be thought of as just a multiplication, which rotates the complex plane and gives electromagnetic, we'll get to why it's in quotes, phases slash charges, right? Since the matrices are one-dimensional, this is by far the easiest group to consider, and its transformations look like e to the I theta. Theta is the phase that we give to the complex plane or the rotation, right? The reason charge is a symmetry is also the most obvious. This phase literally does not affect the dynamics of the system. It's something called a gauge symmetry, and it does not affect the Lagrangian or basically anything you can do to analyze the system and actually get something useful. So at high energies, such as the ones found at the beginning of the universe, electromagnetism and the weak force were actually unified. This is why electromagnetism above was in quotes. While it is true that in lower energy, U1 contributes to charge, at higher energies where the factors are SU3 times SU2 times U1, U1 is something called hypercharge. And at our energy levels, then this symmetry would actually be SU3 times U1, right? So the SU2 term is dropped because there is some, frankly, quite interesting symmetry breaking going on with the weak force. So unfortunately, I do not have time to get into hypercharge and isospin and all the different properties of the weak force, which are I won't say not yet understood, but less understood than something like electromagnetism. So I will perhaps make another video on it eventually as I do find it fascinating. At our mere mortal energy levels, however, there is still the SU1 symmetry, as I mentioned. It just has a bit of a different interpretation. This instead corresponds to charge conservation, and here is where our Noether's theorem, or at least the intuition behind it, comes into play. In fact, after some math, even Maxwell's equations can be derived from the symmetry provided by electromagnetism or quantum electrodynamics, which, I mean, I believe to be a beautiful connection to see how something you probably learned on your first year at university can be derived from something so advanced. It kind of grounds the theory for me in a way. Um, now let's look a bit closer at the maths behind these groups. See, SU2 and SU3 aren't your usual discrete sets, they are continuous, and some very particular matrices that you may be familiar generate them. So what does generating mean? Well, think back to linear algebra. Generators of a group are, in a similar way to basis vectors, a way to represent any transformation within the group. Instead of addition, however, in our case, the operation to combine them is matrix multiplication, or just regular multiplication if the matrices are of dimension 1 or of rank 1, right? Just have one single element in them. So, and being continuous is, if you remember, right, from when we talked about our sphere example, it just means there's like some parameter in there that you can vary. And yeah, that's basically a little bit like a linear combination if you kind of wrap your head around it. Okay, no more teasing. The matrices that generate SU2 are O1, 1, O, O, negative I, O, and then 1, O, O, negative 1, which are the Pauli matrices. You may be familiar with them already. They come up in a lot of places in physics and in linear algebra as well. And the equivalent matrices for SU3 are these, right? The first three are just SU2 with additional rows and columns, and the next are also relatively similar. So the only one that is truly an outlier is this guy right here, lambda 8. And frankly, I don't quite remember why it has that form, but rest assured that these all form the special unitary group. Yep. So it is to truly understand why this is the case, so why these matrices are connected to these kinds of right transformations in the physical sense, right? So why the Pauli matrices are related to, for example, the decay chains and the branching fractions, I would strongly encourage you to look into this on your own. So a book I recommend is Mathematical Methods for Physicists by Arfken and Weber. It was instrumental in the creation of this video. Frankly, I learned a lot about not only group theory, but some more advanced calculus from it. And Wikipedia is a great resource as well, despite what your teachers may say. Oftentimes, the citations are more useful than the content itself, however, though, since Wikipedia is meant to be an encyclopedia, a lot of the intuition can be found in just the text. So I would like to thank you for watching and for kind of listening me to ramble on about these particles that I enjoy a lot, and have a nice day.